This is Daniel Coosbury, and in this video we're going to look at how to construct a confidence interval for the population proportion using statistical methods. So in this instance, imagine a proportion of people, and we're interested in knowing, this is a population, and we're interested in knowing the proportion of people who are in some kind of category, which we have found this with a quite easy looking definition of proportion. So this X represents the number of people in a category, or the number of things. So this doesn't have to be people. It could be like fish or items or something, whereas N is the sample size. And so, like, for instance, if we're polling people and we're trying to find the proportion of people who have red hair, we'd count the number of people who have red hair over the total sample size. And so imagine we've got some population and we don't know everything about the population. The parameter of interest is the population proportion, which we'll denote with a lowercase p. And unless you have all the pieces of information, you can never really know this. It's kind of like the population mean. The best thing we can do is estimate it, but we won't actually know. So we're going to use our parameter estimation techniques again for the population proportion. It's going to involve taking a random sample out of the population and using the best estimate for the population, which is p hat, the sample population, and then we'll use some central limit theorem results to make a confidence interval for the population proportion. So the central limit theorem result for the sample proportion was we had that if n times p is greater than 10, if n times 1 minus p is also greater than or equal to 10, then p has a normal distribution where the mean of p hat was the population proportion, and the standard deviation of p hat was the square root of p times 1 minus p all over n. And so if these conditions are met, then we can use this distribution of the sample proportion to construct a confidence interval. Now, just like with the population mean and the sample mean, if you have something normal and you subtract the mean and divide by the standard deviation, you find the z-score, so to speak. You take p hat minus p, divide it by this thing, you get something that's standard normal, which is going to allow us to use the standard normal critical values when we do our confidence interval. So this is a lot like when we're looking for a confidence interval for mu, and we know what sigma is, we can use the standard normal stuff, the z's, as critical values. So this box over here then, that's not a good line. This box over here then is the pieces of the 100 times 1 minus alpha confidence interval for p. So it has two parts, just like any confidence interval. The point estimate is the single best estimate of what p is, and we're going to use p hat as the point estimate, where x is the number of items in the category and n's the sample size. So that's going to be the middle of our confidence interval, and that's pretty easy to find. And then the margin of error is going to have a critical value from the standard normal distribution. So this should look familiar. It's a critical value from standard normal. And then that depends on what alpha is. And then it's going to have the standard deviation from p hat's distribution multiplied together. So it's going to be this times all that using p hat will be your margin of error. So this will be the thing that we'll have to compute. This is pretty easy to find, but you got to do x over n to get there. So that gives us the total confidence interval for p. So this whole slide kind of sums everything up nice and neat. If the central limit theorems are met, which are n times p is greater than or equal to 10, and n times p, 1 minus p is greater than or equal to 10. So this and is important. Both of these have to be true. Then the confidence interval is given by this guy right here. So p hat plus or minus the margin of error. It's also written as the lower endpoint and the comma the upper endpoint, if you want to see kind of down there. So this is the whole thing, the whole confidence interval. I'm going to show you how to do this in a separate video, but before I do, from this formula we can do a little bit of rearranging. If we're interested in reducing the margin of error while having the same confidence level, there's some restructuring of the formula we can do. So let's start by calling the margin of error m now instead of m. I'm sorry, m instead of e. So this is the same thing as E, but we're just calling it M for a moment, where this is the margin of error. M is equal to this stuff. Then if you do a little bit of algebra, and you want to set the margin of error equal to something, then the minimum sample size that you need to get a confidence interval with this margin of error is going to be this, used by this formula right here. So in other words, you're going to know what p hat is already. You're going to get z sub alpha over 2 based on whatever confidence level you want. So this is based on your confidence level or your significance level. So like you can go into this thing, I want 95% confidence, so alpha's 0.05, and so this guy would be 1.96. So you could say I want this confidence level, and then you could say I want this margin of error. Wow, I do not know what just happened. Oh, okay. So this is your margin of error. And you go into this problem saying, I want my margin of error to be like 0.5 or something smaller than that. And I want my confidence level to be something. Notice you square all this stuff, and then you multiply it times p hat times 1 minus p hat. And then you're probably going to end up with a decimal value, a number with a decimal at the end. So once you get this, round up to the next number, because this is talking about the minimum sample size you need to get a confidence interval with a certain margin of error. So if it's a minimum, so for instance, let's just say that n is equal to, I don't know, 234.14. If that's your minimum value, that means you technically need more than 234. You need a little bit more than that. So let's round that up to 235, just because we're talking about a minimum. So this means I need 234 and some change, so round that change up to the next whole thing, and that'll give you your minimum sample size. So I'll do one of these problems for us, and let me jot down this formula right here. So we're doing p hat times 1 minus p hat times z sub alpha over 2 all over m, and then we're going to square that, whatever that is. So in a survey of 800 music teachers, 632 say that music education has a positive effect on academic performance. Estimate the sample size needed so that a 95% confidence interval will have a margin of error of 0.025, so like a 2.5% margin of error. So we're going to use the sample size formula to do that. Sample size formula, we need to find the critical value. They're already given the margin of error to us, but we need to compute p hat as well. So I'll start with p hat. That's the number of people in the group. So the group is the people who think music education has a positive effect on academic performance. So that's the 632. The total sample size is 800. And I can compute that real quick. 632 over 800. And I get 0.79. So my p hat is equal to 0.79. And then if I'm doing 95% confidence, my alpha is equal to 0.05. And under the standard normal distribution, that means we're doing z sub 0.05 over 2, or z sub 0.025. And that's one that comes up a lot. That's critical value is 1.96. You can find that in the table or use inverse norm to find that value. But the one with 95% confidence shows up a lot. It's that number. So that means we can plug these things into the formula now because we also have the margin of error there. So we've got 3 things that go in the formula, and then we just got to do the formula. So n is equal to 0.97 times, I'm sorry, that's 79. Wow, backwards. 79 times 1 minus 0.79 times z sub alpha over 2, which is that, 1.96, all over m, which is 0.025, and those two numbers are squared. So I'm going to try to type all this into my calculator, putting parentheses where they're supposed to go. Let's see if I can make it nice and big. I'm going to put parentheses where they're supposed to go. So I'm going to do 0.79 times 1 minus 0.79. And then the next part I'm going to put in parentheses too. The 1.96 over 0.025. I close parentheses and I hit the square button. It should just square that thing. So the way the order of operations works it's going to do the exponents first. Well, I'll do the things in parentheses first, and then the exponents, and then the rest of these things are multiplication. So multiply and multiply. So that should come out good. So this answer is 1019.7. But we're going to round up every time we do this. Regardless of what the decimal is, we're going to round up to the next whole number because that's not a whole number. So we need 1,000 people to get a sample, to have a margin of error of 2.5% with 95% confidence. So that's how that formula works. It's a little messy, but like other confidence interval formulas, you only need these three things. You need that, you need that, and you need that. The things I circled in black, and you can do this. So that's how you construct the confidence interval. And in another video, I'm going to show you how to use this formula to actually make confidence intervals for the proportion.